Machining through involute profile gears on a milling machine with standard cutters. First method, using a plain slitting saw. This method is a transposition of the one used to cut gears on the shaper with a plain parting off tool, as described in my previous video. The link is given in the description. A plain slitting saw with rounded profile will be used in place of the parting off tool. Look at the photo. The gear blank is set in a dividing spindle. It's the same attachment I already used on my shaper, simply used here for dividing. The gear to be cut is shown finished machined on the photo, with the main dimensions obtained from the filengrène software. A link is given for it in the description. This will help as the profile shifting and addendum shortening are here necessary due to the small teeth number. This small teeth number was chosen because a great number of cutting passes will be necessary. The slitting saw is working as the parting tool did. The generation movement is obtained by the blanks by circle DB being rolling without slipping on the single tooth rack, being the slitting saw. For this, the transverse movement of the table in the Y direction must correspond to a rotation of the blank. 5 facets will be used for each flank, so 10 for one hole between teeth space and 80 passes for the whole gear, some more in fact for tooth thickness adjustment. This is the price to pay for cutting a gear with a standard cutter on a standard machine, but could be interesting for cutting a small number of teeth or if a CNC machine with a 4th axis is used. The process detailed. The drawing was obtained from a print screen using the filengrène software and some drafting made on this paper. The cutter is shown in its starting position for cutting the 5 facets on the left flank. The total angle through for machining the whole flank is near 60 degrees, so 15 degree increment between each cut. The dividing is obtained from the 72 holes dividing disc, as can be seen on the photo. So 5 degrees for the distance between 2 successive holes, so it's easy to index by 15 degrees or for each part and by 45 degrees for each tooth. Here the gear base circle DB is rolling without slipping on the one tooth rack reference plane, so the transverse through for 5 degrees is the circumference P multiplied by DB divided by 72, so 0.984 mm. The saw is first centered on the blank axis and then moved leftwards by 0.4 mm. Other saw width is 2 mm, but the bottom distance between the left and the right flanks is 2.8 mm. The depth of cut is the whole tooth height, so 6.45 mm. Now the first cutting pass is taken, as can be seen on this video. Now move back the cutter for clearing the blank. Index by 15 degree and move the transverse line by 2.95 mm. Be careful to go in the right direction. Repeat the routine for the next cuts for finishing the first left flank. And repeat this routine 7 times for cutting the 8 teeth left flanks. Look at this photo showing on the left side a cutting pass along the between tooth space left flank, and on the right side the last pass on the between tooth space right flank. For cutting the right flanks, it's necessary to move the transverse slide in the opposite direction by 0.7 mm and not 0.8 as we have to take a span measure WK for adjusting the tooth thickness. Machine now the first right flank and take a span measure for adjusting the tooth thickness by moving the Y in the Y direction before finish machining all the right flanks. The gear was then tested in a running test, the mating gear being also a 8-teeth gear, but cut on the shaper with a trapezoidal tool as already seen in the previous video. Watch this video of the running test. Now the driven gear is 8 teeth but made on a milling machine using a slitting saw and 5 facets. The running is not bad, but we can hear some tinkling. And the power test, of course, we have some tinkling too. Thus, slight tinkling will certainly be removed as the facets rounded during the breaking in process in a well-lubricated mechanism. It must be noted also that with such small numbers of teeth, the contact ratio is small, so the gear set quite noisy. Watch my video for some explanation about the contact ratio. A link is given in the description. Conclusion for this first method: due to the relatively big module, more facets should be welcome. It's not convenient for small modules, as the slitting saw should be too thin in this case, as 0.8 module for maxi for the width. Second method, using standard disc cutters. The need here is to machine gears that couldn't be machined with the standard gear cutters, the set of 8 disc type cutters. So, number of teeth under 12 and gears with shifted profiles. The cutter should be of the rack cutting type, so we will use the last cutter from the 8-part set, being able to cut from 135 teeth to the rack that can be seen on the photo, very near to the rack shape. It's also possible to make a fly cutter having a rack tooth shape. This cutter will be used as the shaper's trapezoidal single tooth cutter, but machining only says 4 passes, so 4 facets for one flank, usually sufficient for our need. It's time consuming as 7 passes for each between tooth space, having 2 flanks, as the first pass is the same for the 2 flanks. Hence, the interest of a CNC machine. But the number of teeth is small and the control and depthing easy with the span measure. You can get a true involute profile, but with facets, for the gear teeth. The gear to be cut, shown finished machine on the photo with the main dimensions obtained from the free filengrène software. The process detailed. This drawing was obtained from a print screen using the filengrène software and some drafting made on this paper. The cutter is shown in its starting position. The angle throw for machining a whole flank is near 40 degrees, so 10 degree increment between each cut. The dividing is obtained from the 72 holes dividing disc, as can be seen on the photo, so 5 degrees between 2 successive holes. So it's easy to index by 10 degrees for each pass and by 45 degrees for each tooth. But here it's the gear PCD that is rolling without slipping on the one tooth rack reference plane. So the transverse throw for 5 degrees is the circumference divided by 72, so 0.436 mm. D being the PCD, equals to the module multiplied by the number of teeth, so 10 mm. Routine to get the good span measure. For this, you need rough only a left flank for the first between tooth space BTS1 and a right flank for the third between tooth space BTS3. So no machining for the between tooth space 2 BTS2. For this, the tool is first centered on the blank, the roughing depth of cut being 2 modules, so 2.5 mm, and the first pass roughed machine. Now move back the cutter for clearing the blank, index by 10 degree, and move the transverse slide by 0.872 mm. Be careful to go in the right direction. Repeat the routine for the next cut for finish roughing the first left flank of the first between teeth space, BTS1. Go back to the starting position for the Y in the Y direction and rotation. And index by 20 degree to go to between tooth space 3 for now machining the right flank of this between tooth space. So machine the first pass for this between tooth space. Now move back the cutter for clearing the blank, index by 10 degree, and move the transverse slide by 0.872 mm. Be careful to go in the right direction, as now the direction is opposite to the one needed for machining a left flank. Repeat this routine for rough machining all the facets of this right flank. It's now possible to take a span measure and to correct the depth of cut accordingly. Go back to the starting position for the right direction and rotation. The cutter is now centered and ready for the finishing cuts. Now the routine for machining all the teeth. The method is to machine, as already seen, the 4 facets for the left flanks of the 8 teeth, and then to machine the 4 facets for the right flanks for the 8 teeth. The gear is now ready for a running test. Watch this video. Now 8 teeth pinion, module 1.25, cut with the number 8 disc cutter with a shifted profile, running with a standard wheel. The by hand running is good. And the power running is good too. The result is very good with no tinkling. Conclusion for this method: it can be used for small modules. The teeth bottom radius is more accurate. It's easier also to manage than the previous one.